Look at any major city from above, and you're watching a massive engine burning fuel. Constructing, maintaining, and operating, the world's buildings consumes nearly 40% of our global energy. That relentless demand for heating, cooling, and electricity makes the built environment a primary, ongoing contributor to global greenhouse gas emissions. To counter this, architects and engineers push toward a radical goal: a structure that produces exactly as much energy as it consumes over its lifespan, the zero-energy building. Because buildings represent such a massive share of total consumption, solving the energy equation here is one of the most effective tools we have to slow the pace of global warming. For decades, the ideal version of this was the off-grid eco-house. The goal was autarky, severing all ties to municipal utilities and surviving entirely on what you could generate on your own plot of land. But true independence requires extreme engineering. You have to prepare for the worst-case scenario by installing massive basement battery banks, fuel cells, or even highly pressurized hydrogen gas tanks just to make it through the winter. Building an island like that requires immense upfront capital. The complex storage systems degrade, components fail, and the physical footprint required makes it nearly impossible to replicate across an entire urban grid. The most reliable way to achieve a zero-emission building is actually to do the exact opposite. You have to plug it in. This is the logic behind the modern net zero energy building, or net ZEB. Instead of chasing minute-to-minute self-sufficiency, engineers balance the building's energy ledger over the course of an entire year. The first step is aggressive energy production. That usually means integrating high-efficiency photovoltaics across the roof, and sometimes even the facade. The second step is eliminating on-site fossil fuels. Instead of a gas furnace, these buildings rely on high-performance electric heat pumps to handle all space and water heating. But tying these two technologies together creates an immediate engineering problem. Heat pumps draw their absolute maximum electricity in the dead of winter, when temperatures drop. A line chart tracks the metrics. In winter, heating demand spikes, while solar production plummets. To balance this, excess summer electricity is pushed into the public grid. Come winter, the building pulls that banked electricity back to run heat pumps. By utilizing the municipal electrical network as a seasonal battery, the property achieves a balanced annual energy ledger, offsetting its winter intake with summer contributions. We can see the system running efficiently in Lystrup, Denmark. This is the home for life, a real-world test case for the all-electric standard. Its roof holds a 50-square-meter solar array. Over the course of a year, those panels generate enough power to completely offset the electricity consumed by the heat pump and every daily appliance. In fact, engineers calculated that over a 40-year lifespan, the home's annual energy surplus is projected to balance out the carbon emissions generated during its original construction. It proves you can reach a zero-energy balance without sacrificing square footage, losing natural light, or daily comfort. But single-family homes are relatively simple. Scaling this math to a commercial office building with hundreds of occupants requires a different approach. That brings us down to Melbourne, Australia, to look at the Pixel building. Office environments face a reversed thermal challenge. Hundreds of running computers and human bodies generate immense internal heat, making cooling the primary energy hurdle. To compensate, the design relies heavily on passive air circulation and smart sun shading to block exterior heat. Then, to meet the massive electrical demand, it supplements the roof's solar array with a row of vertical micro-wind turbines. By tuning the architecture to its specific climate, an office block can entirely offset its operating emissions by treating the structure as a highly tuned energy generator. These structures represent a sharp pivot in urban design. Buildings are transitioning from static resource drains into active, decentralized power plants. While these systems require significant upfront capital, they eventually provide a unique form of financial immunity. Once established, they shield the property from the volatile price spikes and supply shocks of global fossil fuel markets. But the broader advantage goes to the city itself. An entire block of these structures smooths out peaks in demand and adds resilient, localized power back into the public grid. Sustainable architecture doesn't require us to retreat into isolated off-grid bunkers. We find our way toward a climate-neutral future through deep integration, turning every roof and facade into an active participant in a shared electrical community.